Thermal expansion is the phenomenon that occurs as a result of increased energy within a substance as a result of an increase in temperature. The phenomenon causes a substance, usually a solid, to expand and contract based on the behavior of a specific differential equation. The differential equation defines a constant known as alpha, which is otherwise known as the expansion modulus or coefficient for the substance. Even though the dE for the expansion in length, area, and volume are identical, as it turns out, the alpha for area is about double that for length and triple that for volume, not the square and cubed as you'd expect. The differential equation, alpha equals 1 over size d temp, where size is represented as length, area, or volume, is the first order approximation. If you'd like to read about second order approximations of thermal expansion, please refer to the section Higher Order Approximations of Thermal Expansion. For all practical purposes, the first order approximation is all that is needed. It is incredibly important to take thermal expansion into account because not only can it be harmful, like in the case of railroad engineering whereby the railroad tracks can buckle if thermal expansion is not taken into account, but it can also be used to our advantage to make things like bimetallic strips for thermostats, or, even more simply, help you open a difficult jar. We will be exploring 3 different applications of thermal expansion: linear, area, and volumetric, and specific use cases of each. Linear thermal expansion, bimetallic strips.
Hello everyone, my name is Skylar, and today I'll be talking about our project which is on thermal expansion. As you can see, mine starts out quite similar to my 2 group mates as we have the same DE starting, but the big change comes with, instead of having 1 coefficient of expansion, there's 2, because mine's on linear thermal expansion, and more specifically talking about a bimetallic strip, which all bimetallic strip is you take 2 different metals and they're connected to each other, basically a strip of metal, but one side would be, for example, copper or brass, and you flip it over, the other side is steel. The main purpose of this is, as you heat it up, these 2 metals have different thermal expansion abilities or coefficients, and so as you heat it up or cool it, one will expand more than the other, and that will cause the entire strip to bend in one direction. And so, similar to my group mates, you solve it as a separable DE once you add in your 2 coefficients and then end up solving for L to find out the expansion. And so I found 2 pretty cool examples of real-world uses of this bimetallic strip and where this is actually getting applied in real life. And one of them was a circuit breaker, where you simply just have that strip there, and if there's an excess flow of current, then that strip will start to warm up, which will cause the bimetallic strip to bend away, which will open the circuit and cut the circuit, preventing an electrical fire or any other kind of bad things. And then the other one, which is my personal favorite, is old-timey thermostats. And so if you see the picture here, specifically this is just a heating unit. And more or less all that happens is that as the ambient temperature gets cooler, then the strip it'll actually make it contract. But what this will cause is, because of the way it's wound, it'll cause the strip to move to the right until it hits that contact, and it'll close that contact, which will turn your AC on and then turn your heat on. And you'll also see in the next picture there's a little magnet, and so what that does is once it gets close enough, it'll snap into place and hold there. And then that'll stay there, and while it's warming, it won't be able to pull away until it's warmed sufficiently. So that prevents it from turning the AC on and off rapidly, or from there being some kind of arcing current from it being just close enough. And this already very simple design, all you do to set the temperature is you pull the lever on the top, left or right, and all that's doing is it's changing the tension on the coil. And so changing the tension in one direction will make it wait until it's a higher temperature or a lower temperature, depending on the direction, before it cuts on the AC. And if you can see in the picture, the only difference for a unit that has cooling as well is there's another contact on the left. And so if it warms enough, it'll go all the way to the left, hit that one. If it heats up enough, it'll go all the way and hit the right one. And so it's an ingenious design that's super simple, but it utilizes the engineering or the science of thermal expansion.
Area expansion, jar lids, and hot water. I think everyone remembers the first time that they couldn't get a difficult jar open. Some parent tells them to either puncture the lid or just run it under hot water because metal expands when heated and glass doesn't. While not entirely correct, this was likely everyone's first experience with thermal expansion. Glass does expand when heated, but far less so than the aluminum of a lid. We can express the dE as before with land by modeling it as alpha equals 1 over area d10. We ignore the rim of the jar. We get this into a separable form and solve the dE by solving it as a separable dE by integrating both sides. This gives us a dE in terms of temperature, and all we need to do is get it in terms of area, which is a matter of simple algebra. We then get an equation that is some constant times e to the alpha times temperature equals the area. Because the coefficient of expansion for aluminum, about 23 microunits, is far greater than that of glass, around 4 microunits, the aluminum expands far more. It can expand to the point that it can no longer hold the pressure seal, the equivalent of puncturing the jar without lowering its shelf life, and allow you to open the jar far more easily. It is important to note that this same process, in reverse, is what is done in the manufacturing industry to put lids on jars. A heated lid is placed on a jar while a vacuum is being applied. The lid then contracts around the jar, creating a pressure-tight seal. This allows for the product to have a far greater shelf life than it would if it did not have the pressure-tight seal. Volumetric expansion, pressure within a pipe.
So we picked a dE. This dE is representing the temperature and the volume of the object. I will be talking about how a copper pipe can expand and be affected by temperature changes. We have the equation alpha equals 1 over V dV over dt. We start with alpha. Alpha is our expansion coefficient. In this case, it's coefficient of copper expanding. And then we have V, which is our volume of the object. In this case, also, it's the copper pipe. And we also have dV, which is the change in the object's volume. And the dt, which is the change in temperature around the pipe or the pipes. With our equation here, we chose to integrate just like we learned in class, and you all can walk through the steps and see what we've done. Talking again about copper pipes and real life scenarios, the sun being the number one source of heat affects copper wires in every aspect, like air conditioning units, you have bathroom pipes, electric wires, car motors, all those things have copper wires in them, and it being affected by the sun and the heat, it will make the copper expand, which could make you lose pressure inside of equipment and things like that.
In conclusion, we can see that thermal expansion is not only an integral part of engineering, pun absolutely intended, but also an essential part of our everyday life. Without thermal expansion, we would not have many of the thermal protection systems that exist throughout our homes, and without the material science engineering that goes into building structures, many structures would fail long before they would have if thermal expansion was just taken into account. It is important that we continue to study the topic in material science to see what more it can do for us.
That's why we thought this project would be very important and very eye-opening on how copper wires and things expanding in general with this differential equation can help us.
We all decided to do thermal expansion as a project because not only is it an interesting topic that we're all familiar with, but it's also an important topic. Even though the differential equation is fairly simple, the science behind it is not. And the simplicity of it does not change how important they are to study as a topic of engineering or even for at-home applications. So maybe next time you use your thermostat or have to open a jar or use your pressure washer, it'll be a little bit more interesting. Thank you guys for listening and joining us on this presentation.